requests. Anything at all you'd like to hear, just... Not yet! I'm not through talking! As I was saying... Thank you. It was nothing, really. How about some applause for my assistant here? All right, enough for him. How about some more applause for me? Put that thing away. Wise guy, eh? I taught him everything he knows, and this is how he... What the... This is the most ridiculous... You're not fooling anybody. He can't see anything out of those things. What? So, think you're funny, don't you? Yeah. Seriously, folks, he can't see, but some robots can see. Take this guy, for example. He's got laser eyes. He goes around measuring critical stuff on the car body. And big as he is, he's very delicate. Accurate to the nearest 10,000th of an inch. Of course, most robots don't need to see. They just remember where things are. This is robot school. This NC Painter robot is learning the shape of a new body. A new car body, that is. And with instructors like that, school don't look so bad.
Hello and welcome to MicroLive. That was part of the General Motors exhibit at Walt Disney's Epcot Center in Florida. It gives the impression that robots really have human abilities, and given a pair of laser eyes, they can see anything. Well, is this even approximately true? Today's program is about robots, what they can do, and what the main challenges are for scientists and engineers designing them.
Well, of course, both the bird and the robot were computer-controlled figures. All they were doing was executing very precise, highly defined movements in time to a synchronized soundtrack. Here, we've got a small industrial robot. So, let's see what it can do. Put it through its paces. It's got, in fact, 6 joints. They're called the waist here. Then there's the shoulder, the elbow, the wrist, which is actually quite complex. It can do 3 different actions: roll, pitch, and yaw, they're called. And it's even got a hand, there it is, which can clap. Now, each of those actions is driven by its own motor and controlled by its own microprocessor. Well, we've also programmed it to perform a typical sort of task which a robot like this might be used to do in industry. Here it's simply picking up objects from a very precise position and moving them to another very precise position. Now, the movements may look very simple, but in fact they're actually quite subtle. It's picking up those blocks very slowly, gently, then it accelerates and decelerates, and again puts them down gently. No prizes for guessing what it's building. It uses those 6 motors in a very precise combination, and it's that precision, and of course all the electronics, that make it so costly. This one, in fact, would set you back £30,000.
Well, if you want to learn about robotics, something much cheaper will do. For £175, you can get a teaching robot like this one. It runs on a single micro, and you can see here one of the devices that tells the micro how far this part of the robot has moved. There are a series of marks on these wheels which reflect infrared light, and a sensor counts them. To tell it what to do, the instructions are written in a simple control language, rather like BASIC. Fred's robot uses a similar language. Well, since the 70s, industrial robots have been used for simple, repetitive jobs, especially the ones that people don't like doing. One of the latest applications in Britain is testing parts for the Ariane space rocket at British Aerospace's plant in Stevenage. 2 ultrasonic probes on the ends of the robot's arms move over every inch of the surface of this heat shield, checking it for defects. They can follow the curves of the shield without any problem. Before the robot was used, it took man many hours to do the same job, and not nearly as well. Industrial robots come in many sizes, and they must all carry out a series of movements over and over again with great precision, even when they're carrying large weights on the end of their arms. We decided to put this to the test using one of the largest industrial robots around. We fixed a pin on the end of the robot and then introduced it to one of nature's frailest objects, an egg.
Pretty good, hole in one. Now, the main problem with this kind of setup is it can't deal with uncertainty. For example, if I took one of these blocks away, like so, the robot still thinks it's there and it will blindly go on through its actions. And of course, from here on in, we're right up the creek, dropping blocks all over the place. Now, you might think that adding a vision system would solve that problem, but in fact, interpreting images is very complex. Mike Brady, you're a robotics scientist. What's the problem about recognizing a simple object like a brick?
Well, there's no real problem for us in recognizing simple objects like this. After all, we know all about cubes. We can determine their color. And even if we were to place an object like this in a cluttered background, we'd still be able to distinguish it on the basis of color, on the fact that we can separate objects in depth and so forth. The problem is that robots don't really have the ability yet to make much sense of color, nor can they do very much with regard to depth. So they end up by taking a black and white image like you see on the screen.
And then it's very difficult to find our brick, let alone recognize which one we're after. What's the solution to that?
Well, as so often is the case in engineering, you solve the problem by essentially avoiding it. You try to separate out objects and you place them on a separate high contrast background where the robot can move and pick them up.
Right, now that may seem to be ducking the issue, but in fact that's the approach we saw on MicroLive a few years ago when we launched a competition to devise a ping-pong playing robot. And as you can see, in the MicroLive studio, they still had a long way to go.
If I count down 3, 2, 1, go.
Oh, what? It tipped it.
Very
it tipped
nearly,
it.
very
8 out of 10
nearly.
for the smash, but how did it see the ball coming?
It didn't see the ball coming. This one, we cheated a little. We used a bit of guesswork on where the ball would arrive. But
Right.
it has got a vision system.
And come the day those two will be joined together, the
they've
vision
got to be.
system and the action.
They've got to
Right.
be.
What a fraud. But at Bell Labs in the United States, they took up John Billingsley's challenge, and this is what they produced. Now, Mike, avoiding all the mathematics of the ballistics here, how is the robot detecting where the ball is?
Well, rather like in the case of putting our block on the light table, we've set the table tennis ball up against the black background of the person wearing the black muslin shirt. We've simplified the table tennis table. We've got a TV camera above the table and one behind the bat. And so it can track the ball in those two cameras from binary images, and then with very simple trigonometry and arithmetic, rather like triangulating for a position of a yacht, it can find the position of the ball in space.
Right, well, it seems to work in the laboratory, and in real factories too. Vision systems depend on having a relatively easy feature to search for, a bit like that white ping-pong ball against black. Here, Freff reports from America on one advanced industrial application.
Two men install a car windscreen. Almost without thinking about it, they're communicating, taking cues from each other and from the production line as it stops and starts. They're governed by the speed of the line, which gives them only a small window of opportunity to press home the glass. They do this with human skills, which we take totally for granted. Recently, at the General Motors Buick City plant near Detroit, they've automated this skilled but tedious part of the car production process. Here, instead of men, robots cooperate with each other in what's known as a flexible work cell. On the left, a group of 4 robots prepare windscreens for a range of cars of different shapes, sizes, and colors. On the right, a vision system looks at each car as it comes along the production line and tells one of the robots exactly where to place the windscreen, a slightly different position for every car. And round the back, a similar group of machines puts in the rear windows. But the system isn't yet smart enough to load the right windscreens in the right order for the cars as they arrive. A carousel still needs a man to load it. This takes the windscreen to 3 robots in turn, which prepare its edge with the chemicals which will glue it to the car. If the glass weren't held firmly in the right position, these robots wouldn't have any idea where it was. They're blind. But no human would spray so evenly, or so quickly, or so tirelessly throughout the day. Each robot has its own computerized control system to guide its complex movements in space, and a different program for each size of windscreen. So how do the men and the machines know in what order cars are coming along the production line? Every car on the assembly line has one of these attached beneath it. It's a short-range microwave transmitter programmed with a numeric code which identifies what kind of car it's supposed to be when it comes out the other end of the plant. This one might say, "Hi, I'd like to be a red Buick LeSabre two-door with black seats, a thermal rear window, and the following options." As the car moves down the assembly line, receivers in the floor pick up this number, and the men in the machines in each workstation act accordingly. A massive cabling carries messages between the machines. It tells them when to start or stop, which program to run, and brings the latest news from the various sensors. Software was developed here specially for this work cell. The most difficult thing was tying in the vision system. That's the unique feature. Using a number of black and white cameras, each car is viewed from a number of angles under very bright and very even illumination.
The vision has to be within 3 to 4 millimeters accuracy when they load the windshield in the car. It's looking for the contrast and the edge around the windshield opening. It focuses in on that point, and there are 4 different cameras that look at that point, giving us a 3-dimensional picture of the car edge.
What you're seeing here in real time are the lines of high contrast that the computer has picked out from each black and white image. From this massive information, it has to identify the edges and angle of the window opening in each view, then use a bit of 3-dimensional trigonometry to tell the robot precisely where to move.
Now, with the ping pong ball, Mike, you're looking for a single point in space. That looks to me to be much more complex, is it?
Not particularly. After all, General Motors went to a great deal of effort to simplify the contrast colour of the car, the lighting. They had 2 or 3 cameras sprinkled about. They were looking for a very simple feature, and again, to triangulate, to find that windscreen opening in space, much like the ping pong ball. In both cases, they needed vast amounts of computing.
Right. Let's move back to our problem here with the block amidst all the clutter. Here is a remarkable piece of film which shows a computer solving that problem.
Well, here you can see an example of a bin full of castings with one stray object which has to be removed because the computer only knows about one kind of object. Central to the operation of the program is that the computer has a model inside its memory of that casting. In this case, it looks like a computer-aided design model. The robot uses a laser ranging system to compute explicit depths, so solving the tough vision problem we saw earlier. Here the edges are depth edges where the surface intersections on the objects.
It's only got the one eye, has it?
It's only got the one eye, but it's computing depth. Now what it's doing is finding little edges and trying to match them up against its model that's stored in its memory. And every time it finds one, it makes a hunch about where a model is in the memory of the computer.
So then it tests that hunch against other things. It predicts that there must be another edge over there and then tries to fill it in.
That's right. And the more information it finds, the more it can narrow its hunch until eventually it fills in an entire object, like the one you've seen here. And of course, once it's filled in an object, it'll go and verify as far as possible what it can see. Here you can see it testing edges, filling in models, then going around finding another edge that looks particularly as though it would support a hunch, and then filling in another model and so forth until it's found and accounted for all of the objects that seem to be in this particular bin.
But it can only deal with those particular objects?
It can only deal with those particular objects. You'd have to teach it a new object for a new bin.
That looks to be very sophisticated. Is that state of the art?
That's pretty much state of the art in industrial vision these days, yes.
Right. Thank you, Mike. We'll come back to you later.
Well, the main economic reason for using robots is to be able to make automated industrial processes more flexible. That means being able to change what you make without having to change all your machinery and start all over again. One of the frustrating problems in industry is the long time it often takes between designing something and getting it into production. For example, this is the old way that biscuit molds used to be made. An enlarged drawing of a biscuit is stuck on the surface of a block of brass and carefully cut out by a skilled craftsman. He then follows the contours of this giant mould using a device something like a child's pantograph. Through a series of mechanical links, this reduces everything down to the size of the final biscuit mould. 100 of these need to be cut out to make one biscuit roller, and that used to take as long as 3 months. By designing the biscuit on computer-aided design equipment, the whole process can be speeded up. The designer defines the exact dimensions of the mould on the screen. The system then sends the instructions for the way the mould is to be made directly to a computer-controlled robotic milling machine. The biscuit moulds can be cut directly on the roller, a row at a time. All this has cut the time taken to make a roller, and therefore the time to make a new biscuit, from 3 months to as little as 3 weeks, giving this company a cutting edge over its competitors. If new products can be designed quickly, flexible equipment is needed to make them. This robot machining centre can do a range of different jobs. Here it's finishing off a plastic moulding, which is part of a switch housing. It can grind and drill in a variety of ways which are determined by the robot's program. If the design of the part alters, all you need to do is to alter the software. If designs can be changed easily, and the machines are capable of making a range of different things, the next thing is to be able to move materials about the factory in a flexible way. That means programmable conveyor systems like this one, able to move any parts to any machine. This factory can make many different parts, and make just a few of them as quickly and as cheaply as making a large number. To educate engineers about the design of advanced manufacturing setups, models like this are being used to build and test prototypes, making it quicker to get the real thing into action. This one, built out of parts you can buy in any model shop, was actually used to design part of a Volkswagen car plant. The control software was developed on this, and all the bugs ironed out before the real thing was built. Well, people have been predicting the renaissance of industry using advanced manufacturing techniques like these for some years now, but it hasn't quite happened yet. One of the things which has held things up has been incompatibility. The inability of one computerized machine to communicate with another, as Freff found out back in that General Motors factory.
If you look below the surface of the automation in this General Motors car plant, there are clues that this is still far from the promised land of integrated, flexible manufacturing. Bits of paper with special instructions still accompany each car. Paper still duplicates the information sent out by the transmitter fitted underneath each body, because the transmitter only gives information to some parts of the production line and not to others. And other information appears on screens to be read by the men on the line. And in the central computer room, an island of quiet in the middle of the shop floor, various incompatible computer systems look after different parts of the car-making process, tracking orders, scheduling the work, controlling the conveyor systems, and so on. We found Prime computers, IBM and DEC systems, and tandem terminals sitting side by side, unable to exchange data with one another. Almost all the computer-controlled machines in the plant have to be programmed and reprogrammed locally. They aren't yet linked to a central computer, or to each other. GM has over 40,000 intelligent devices in its various plants. Automatic loaders, code readers, robots, vision systems, and more. The difficulty is that very few of these devices actually talk to one another, fewer than 15%, because they're made by different manufacturers in different countries, and their hardware and software is typically incompatible with everything around them. GM feels that this lack of standards is holding up the development of computer-integrated manufacturing, so it's flexing its industrial muscle and forcing equipment suppliers to conform to a new standard called MAP, the Manufacturing Automated Protocol. MAP is not a programming language. It's a way of passing data between machines of different makes, and it should make it easier for machines like these to be programmed remotely with information sent from a central computer or even directly from computer-aided design equipment. By making such links possible, GM hopes to cut the time taken between design and manufacture by as much as 50%. MAP could replace all of today's special cabling and interfacing with a single coaxial cable to connect all the machines together. The aim is tighter control of the entire production process.
The nearest analogy to MAP is the agreement that countries have made for interconnecting international telephone calls. It simply enables people to talk to one another, and that's all. It doesn't solve the problem that they're all speaking in different languages. But MAP is a start, and many manufacturers are adopting it to get better information flow throughout the factory, giving tighter controls and new ways of reducing costs.
It's going to be a long time before most of the assembly jobs in a car factory are automated. But there are savings in getting the parts to the shop floor only when they're needed. So here, GM uses a controversial system called just-in-time.
In the past, we've had huge warehouses full of material. We've had stacker cranes full of material. Today, we try to keep our processes in action with a minimum amount of material for an hour or a few hours of action in a particular process.
Just-in-time means constant deliveries, with big penalties for any manufacturer who delivers late. This truck is delivering seats. Usually, they're unloaded by 2 robots. One uses a barcode reader to identify the seats and to unload them in the right order, straight onto a conveyor right by the production line. But when MicroLive was in the factory, the robots broke down, producing a real dilemma for the engineers. With only a few seats left on the conveyor belts, there was a danger of the whole plant having to shut down. Repairs had to stop, and men with forklift trucks were called in to unload. The robots normally unload several times faster than these men, but machines are liable to break down. It's hard to see how MAP could have helped this situation. It's hard to make cars without seats. Automation clearly has its limitations, and often it's the flexibility of the men, not the machines, that saves the day.
Yes, well, men can still do a lot of things that robots can't. But let's have a look at some of the new research into giving robots greater flexibility. Mike, let's start off with the grippers, the hands. What's new?
Well, in our first video clip, we can see a robot hand that's been developed by Ken Salisbury, first at Stanford University in the United States and subsequently at MIT.
A lot of flexibility there. It's double-jointed, isn't it?
Extraordinary flexibility. The hand was actually designed to be able to grasp an arbitrary object. It doesn't know anything about this can, but to be able to move it in any arbitrary direction and impress an arbitrary force on it. There was no attempt here to mimic human hand design or human hand control.
Is there any point in mimicking a human hand?
Yes, indeed. As the next video clip shows us, if it were not for the example of the dexterity of human hands, we may well have given up the task of trying to build robot hands with similar dexterity years ago. Here we see a system which has got 4 fingers. Each one of those fingers has got 4 different actions or joints, and each of those joints is pulled by 2 tendons, much like in a human hand. So there are 32 actions in all, unlike the 6-motion robot that we saw earlier in the program.
And the motors are remote from the hand themselves?
Yes, indeed. They're down that rather little marionette arrangement that you can see on the right of the picture there.
Why is it twiddling its fingers, Mike?
Well, really as a demonstration to show just how fast a modern robot dexterous hand can go, because for a long time people suspected that you'd never be able to build very fast hands like human hands. You'd always have to put up with very, very slow and rather cumbersome devices.
Right, and it flicks it away very deftly. Now, those hands had no sensors in them, did they? They were just moving to predetermined locations.
Absolutely, and indeed the attempt to incorporate sensory information, for example, to avoid collisions, as in this clip of film, which again comes from Stanford University in the work of Osama Khatib, illustrates the incorporation of control into planning trajectories for a robot. The kennel is being viewed from a TV camera above. Of course, the system doesn't know anything about Snoopy or kennels or anything. It just sees
recognises an obstacle.
A black blob, and if it's there, it'll navigate around it. If it's not, it'll go back to its preset path. Now, this system isn't restricted solely to visual information. Here you see force information being used to control the robot rather than vision.
It's not being pushed up, is it?
It's responding to very delicate forces as delivered through a sponge which is being held by this operator here.
And it's hardly being deformed, that sponge.
It's hardly being deformed. This has got tremendous reactivity to external forces.
What's all this handshaking about?
Well, the basic idea is that much of assembly and much of machining these days consists of, as it were, bringing robots in graceful collisions with the external world, as for example in this scrubbing application, or in here in following a contour. So we want to be able to program forces. Here's a rather different one though, where the work of Jim Trevelyan in Western Australia, where we have a little sensor that appears to be simply flying at about 1/8 of an inch above a human hand that's moving around.
Why would you want to do that?
Well, the secret is in the little end effector there, which looks like a comb. Indeed, it's a cutter. This is a robot for shearing sheep, and what it does is it goes in and it's attempting to cut the wool.
That's a real live sheep, isn't it? I saw it twitch.
It's a real-life sheep, all right.
We're not going to see buckets of blood, are we?
I doubt that you'll see buckets of blood. You actually probably can see one slight nick, but you should understand that this system cuts a sheep about 1/100th as often as a professional sheep shearer would.
That's a moving, breathing sheep.
Yeah, the key to doing this problem, in fact, is not only to have this sensor which is gliding over the surface of the sheep cutting, but to have a model, a kind of CAD model, geometric model of the sheep, which is used to plan paths, but where the sensor essentially adjusts its path to glide over the surface of the sheep.
A flexible model.
Indeed, a flexible model.
Now, all those robots we saw, including that one, were routed to the spot. What's happening about robots moving around?
Well, here you see an example of a walking robot, although wheeled and tracked robots have also been built. This is a system that comes from the University of Tokyo. It's the first robot that was unstable in the sense of falling over when you turn the motors off, but can stand upright when you turn the motors on.
Now, hold on, Mike. I've got a son who has a clockwork toy that seems to do exactly what we're seeing here.
Right. Hold on, Fred, you're wrong. The basic idea is that in your child's toy, the centre of gravity of the system is deliberately pitched low so that it's stable and it won't fall over. Here, and in particular in this one, which is the marvellous work of Mark Rabert, first of all at Carnegie Mellon and more recently at MIT in America, of a system that's trying to balance. It has a very high centre of gravity and stopping this thing falling over.
Yes. I wouldn't have thought that was possible.
No, well, nobody did actually until about 5 years ago, till Rabert showed that you could in fact build a balancing machine.
Why would you want a hopping robot?
Well, the idea of this system is that balance is central to ordinary human or animal motion, such as walking or running. Here you see a two-legged version of the same thing. It's actually two of those one-legged controllers that we saw in the previous video clip. This thing is alternately being a left hopping machine and a right hopping machine, and by switching between those two legs, you can gain the effect of running.
It's detecting a tilt, and then it's responding to it either by correcting it or by, in this case, it's building on it.
That's right. Running, in a sense, is controlled prevention of falling over. And it's shifting its centre of gravity and adjusting its stride pattern accordingly. And by changing it in various ways, you can increase the speed of the robot. Here it's reaching somewhere between 12 and 20 miles an hour.
Took a tumble there.
Indeed. This is a four-legged robot, which is built from the two-legged robot in pretty much the same way as the two-legged robot was built from the one-legged robot. You pair off couples of legs, here the diagonally opposite legs, to provide one of the so-called gaits of the mobile animal. If you choose different pairs, you get trots or bounds or what have you.
Have you taken these movements from nature? It does look as though it's been modelled on a horse galloping or trotting.
Well, actually, engineering and the studies of human and animal motion are informing each other here. We didn't know very much about human and animal motion until we started to build the engineering devices.
I can start to see a use for a four-legged machine, because rough terrain would obviously need something that could adapt as it moved.
Indeed. The principal application of these kinds of walking machines is, in fact, to march off the road and into forests for lumbering, particularly in the Soviet Union and Canada.
This research all looks very exciting, but what's next? How do you pull it all together?
Well, what we've seen are a whole series of very exciting devices, but what we really need to do now over the next few decades is to bring the kind of very intelligent controlling software that we get from artificial intelligence and use it to control some of these devices.
Oh, good luck, Mike. Thanks very much.
Well, that's about all for this week's MicroLive. By the way, if you were watching last week's programme, you may be interested to know that John Wilson won the User of the Year award at the Rita annual dinner. Finally, if you think robotics have been taking 2 steps forward, as you'll see, it's also been falling over backwards. See you next week.